Hello students, welcome back. Finally, let's go back to Fermat's theorem and let us prove it. By the way, the proof of Fermat's theorem will be reproduced in abstract algebra, and there the proof will be much easier because we are going to use the techniques that are a little bit higher up. This proof is not the most efficient proof. Remember that. So if you get lost here, then there will be a chance to recapture this in abstract algebra. Okay, anyway, let's come back to this. Fermat's theorem. If p does not divide a, then a to the p minus 1 power is congruent to 1 modulo p. And here, as I highlighted in green, p not dividing a is the same thing as a is non-zero modulo p. Therefore, we get the second line. If a is non-zero, then here, in this identity, in this congruence, multiply a to both left-hand side and right-hand side, and then we get this one here. A to the p power is congruent to a. Now, if a is 0, then we have just 0 is congruent to 0. No problem there. So this thing works all the time. And that's just a trivial application once we got here. So let us focus upon the first line. Also, we showed this this alternative aspect of p not dividing a, which is the same as a is non-zero mod p. So I don't need this anymore. Let's focus upon this only. All right, let's prove it. And we have multiple steps. And step 4 is just an extension from 1 to 2. So that's no big deal. And step 3 is really ingenious step. Step 1 and step 2 are just preparations. All right, first preparation, assume p does not divide a. Yeah, all right, that's the assumption. And let us define a subset capital A of z like this. 0a, 1a, 2a, 3a, on the way, all the way up to p minus 1a. And if p had been, if p divides a, then all this would have been just congruent to 0 mod p. But p does not divide a. Under that assumption, it turns out these are all distinct mod p. Why? If any two of them are the same, RA and SA are the same mod p, then the cancellation rule applies because p does not divide a, or equivalently speaking, a is non-zero mod p. So cancellation applies, so we have R is congruent to S mod p. But here, R and S are just integers from 0 to p minus 1. So this congruence, as a matter of fact, gives us equality. Consequently, everything here, all these are distinct. So we have p integers that are all distinct from each other modulo p. Now, can you think of another subset of z that consists of p integers that are all distinct from each other mod p? That's zp. And we went through that already. zp, that just gives you the congruent class through the remainder classes, through the division algorithm. We went through those already. So zp consists of p integers. They are all distinct from each other modulo p. In short, this a and zp must be the same modulo p, of course. So if you compare each individual numbers, then they're not equal to each other, but they must be all congruent to each other. the total P separate classes, and that covers everything because it's coming from the division algorithm, and that classifies the entire set of integers completely. And then this one covers all P classes, so they must be the same. So A and ZP are the same mod P. And then here we're going to go one step further. We're going to remove this 0 and this 0, because 0A and this 0, those two are congruent, and consequently these are congruent to those, and then we're going to name those as AX and ZPX. Actually, this is not X, this is actually multiplication symbol, and it's a shorthand of non-zero elements. So take non-zero elements, remove all those zeros. Okay, we have AX and ZPX already here, so let's not reiterate them here. And then there's no reason to eliminate those completely, so let's just put those normal gray. And then compare this AX and ZPX. They must be congruent. So this A and ZP are congruent, and then among those 0 and 0A, those are congruent, those are out. So rest will be congruent to these. And then as for the order, they must be all jumbled up, but that's okay. All right, so we have all the preparations done for our main step. So non-zero elements of A and non-zero element of ZP are all congruent to each other, but order may be all jumbled up. How do you get over those jumbled up order? One way to do that is to multiply them all. If you multiply them all, multiplication is commutative. So 1A times 2A times 3A times order of the P minus 1A will be congruent to 1 times 2 times 3 times L2 P minus 1. You see, 1A may be congruent to something here, 2A may be congruent to something over there, and 3A is congruent to something, and they may be all jumbled up. But it's okay because multiplication is commutative if you multiply them all. And then here, if you multiply them all, they must be congruent. Consequently, we get P minus 1 factorial a to the P minus 1 power is congruent to P minus 1 factorial. All right? Now, can we cross out P minus 1 factorial? The answer is yes, we can, because none of them here, this P minus 1 factorial consists of the factors 1, 2, 3, 4 up to P minus 1, and none of them there is congruent to 0 mod P. P does not divide P minus 1 factorial. P is relatively prime to everything from 1 to P minus 1. So we can use this cancellation law. We end up with a to the P minus 1 power is congruent to 1. You see, we have this long preparation. A is 0A, 1A, 2A, 3A, and so on of the P minus 1A, and getting P integers that are distinct from each other, modulo P. And then another thing, ZP, and also this is coming from the remainder class, so there's no other integer. So this completely classifies the entire Z. So this one and that one are the same, and then remove zeros so that non-zero elements of A and non-zero elements of ZP are the same modulo P. And that preparation there, all those preparations, those two preparations are present to set up this thing here. This is the ingenious step. If you multiply them all, then the ordering doesn't matter. So we end up with P minus 1 factorial, a to the P minus 1 power, and to the right, P minus 1 factorial. After cancellation, we just get 1. That completes the first line. The second line is just trivial consequence. If p does not divide a, then we have the first line, and multiplying a to both left-hand side and right-hand side, we get the second line. And p divides a, then a is congruent to 0, therefore 0 is congruent to 0. So in the end, we have the proof of Fermat's theorem in the original form, modulo p. Now, do you have time to prove Euler-Fermat? Oh, okay, all right, I made a wise decision. Just skip to the proof. All right, okay, all right. If you want to, you can try to prove it, or you can wait till abstract algebra, and there we're going to do this in much more advanced method. Consequently, Fermat's theorem and Euler's theorem both become pretty much one-liner. Of course, in order to get to that level, you have to build up a lot more. But anyway, that's something we are going to do in abstract algebra. So basically, that completes the proof of Fermat's theorem and Euler's extension. And we have a little bit of time left, so let's talk a little bit about pseudoprimes. Optional topic. What do you mean by pseudoprime? Well, if p is prime, then a to the p power is congruent to a mod p. Yeah, that's true. But the converse is not true in general. A to the nth power is congruent to a mod a, and then is n prime. That's no. The composite number satisfies the conclusion of the Fermat's theorem like this, or like that, is called a pseudoprime. And the composite number satisfies the conclusion of this Fermat's theorem for all a is called Carmichael number. And then study of Carmichael number is a big deal, but of course it's too much of a deal for us. This is, of course, undergraduate level course, so let's not go too deeply into that. Let's see, is there anything that's worthy of consideration? Now, these kind of numbers are Carmichael numbers, and it is known that there are infinitely many of them. So these are composite numbers, but it satisfies the condition of Fermat's theorem. A to the nth power is congruent to a mod n. By the way, this Fermat's theorem, the first line, that never works because all of Fermat's theorem says phi of m power, and phi of m, that is not m minus 1, that is never m minus 1 for composite numbers. You see, phi of m is number of positive integers less than m that are relatively prime to m, and m is a composite number, then you have to exclude all its factors and all the other smaller numbers that share any kind of prime factors with m, so it should be less than m minus 1 all the time. So this is always no for composite numbers. But this one, sometimes it may be true, and those are pseudoprimes, and it's true for all a's, and yeah, we have something called Carmichael numbers, and those are like this. Yeah, 5 and 60, so that's not a prime number, it's a composite number, but still it satisfies all those conditions of all the conclusions of Fermat's theorem. Okay, that's about it. Let's not worry too much about those. There's no exercise problems associated with pseudoprimes or Carmichael numbers. But if you want to present it, that's going to be a good topic.